everyone. You guys have already know me. You saw me in the first week also. I was teaching basics of network theory, and we did build few things on MATLAB Simscape in the first week. So I'll be taking the remaining 3 weeks of this lecture of this session. Okay, during these 3 weeks, what we're gonna study is we're gonna work on MATLAB. We're gonna study about vehicle dynamics, like what are the forces acting when a vehicle is moving in forward direction, and we'll build a MATLAB model for a quarter car, not all the four wheels, but only one fourth of the vehicle, just to understand what are all the forces acting in the direction in which the vehicle is moving and in the opposite direction. We're going to build MATLAB model for it, and also we'll study about field-oriented control of brushless DC motor, and we're gonna study about reluctance motor. Okay, so we don't go deep into those motors, but you'll get an understanding. Okay, what is a reluctance motor? Okay, and then we'll jump to control systems. So control systems by itself, it takes more than a week. So we'll go from starting basics of control systems to how to find how to build a controller for a given transfer function. So I'll be covering those topics in the coming 3 weeks. And today, because as Professor Ali has already taught you about AC motors, a continuation to that topic of brushless DC motor is field-oriented control of AC motors. So if you guys have seen, uh, we know okay, what is the difference between a, induction motor and these AC, like permanent magnet or synchronous motors. So in synchronous motor, if you observe, okay, let me share the screen. Just a second. Can you guys see the screen?
Yep.
Yes.
Yeah.
Okay, so if you take any like these brushless DC motor or permanent magnet synchronous motor, the torque equation of these motors is given by this simple formula, okay, which says torque developed in the motor, okay, is equal to the magnetic flux developed by the current flowing through the stators, okay. R is the length of the rotor. Uh, so R is the distance, L is the length. Okay, sine of theta R, theta S minus theta R. Sorry, sine of theta S minus theta R into ns by 2. Yes, into ns by 2 to pi. This is the uh, torque developed by a brushless DC motor. So you have seen the derivation of this equation. Now, if you observe this, okay, if you observe this equation from a mathematical point of view, so there is a sine function included in this torque equation, sine of theta s minus theta r. So angle of the stator minus angle of the rotor. We know this in synchronous motors, okay, say like if you take the broad classification of these uh, motors, okay, so can someone say what are the two types of classifications of these motors based on the power supply?
AC and DC.
Yes, DC motors and AC motors. So when it comes to DC motors, again, there DC motors means we provide DC current to the motor, then we call it as a DC motor. If we provide AC power supply to the motor, then we call it as a AC motor. As simple as that. Again, in the DC motor, there is two types of classification. One is self-excited, okay, another one is separately excited, SEP, separately excited. So what is this self-excited, separately excited? If you use one power supply for both the armature and the field, then it is called self-excited DC motor. What is this armature and again field means? Again, you need to come back to the definition of the motor. What is the definition of the motor is when current carrying conductor is placed in a magnetic field. So there are two things here if you observe. So one is a conductor which is carrying current. The second one is the magnetic field. So there are two forces acting upon it. When current carrying conductor is placed in a magnetic field, then there will be a force acting upon it. That is the definition of a motor. Now, let's not go into details of how the coils are everything is built. But if you observe the definition, there are two things. Okay, current carrying conductor. Okay, current carrying conductor. Okay, another one is magnetic field. Okay, so current carrying conductor is very simple, a piece of coil which carries current. Okay, now magnetic field, it can be either permanent magnet or it can be an electromagnet. Again, if you want to use an electromagnet, again you need a power supply. So, so when for developing the magnetic field and for the conductor, okay, and for the conductor, if I use same power supply, then it is called self-excited DC motor. If I use same power supply for for the current through the conductor and for also the magnetic field, then you call it as a self-excited DC motor. Then what is separately excited DC motor? As the name indicates, you have two different power supplies for the conductor and for the magnetic field. Then it is called separately excited DC motor.
Sorry,
Yes,
professors, I just joined.
you can call me Narendra. Yeah,
Narendra. Okay.
please. Yeah.
All right. So we are talking about uh,
I'm
self and
just
yeah. Okay.
yes, I'm
Yeah.
not actually going into details. I'm just recapping about motors so that I can jump to my topic. Okay.
Okay. Okay. So general
Yeah.
motors. Okay.
So
Got it.
yeah, General Motors. So not going into the details because professor has already covered. Okay. I'm just
Got it.
rewinding
Got it.
what you have gone through.
Okay.
Okay, so motors classification AC and DC. DC again self-excited DC motors and separately excited DC motors. Here too you have two different power supplies. Here you have only one power supply, but for the magnetic field and for the conductor. So this is DC motors classification. Here there are again three classifications. Let's not go into detail of that. Now coming to AC motors, basically AC motors are of two types. What are they, guys? You already know. Can someone say?
Synchronous and
Synchronous and
non-synchronous.
asynchronous.
Yes, synchronous and asynchronous. Okay, so as the name indicates, synchronous means they are in sync. Asynchronous means they are not in sync. What are in sync? Okay, what are in sync? The two things which are in sync are the rotating magnetic field and the conductor which is rotating, or the shaft which is rotating, or the rotor which is rotating. Again again in the for motor you need a magnetic field and you need to place a current carrying conductor into it, then only the conductor will it will there is a force acting upon it, which is nothing what as the force is acting upon it, it will move, and that's what we see outside. The output is a mechanical force, right? Again, in synchronous, what happens is, so by using certain winding technique which is recommended by Tesla. Okay, we do stator winding. Because of that stator winding, the particular kind of winding which we do, okay, what we did is we developed, whenever we provide a AC power supply, we developed a state, the coil is wound in a such a way that the magnetic field is rotating all the time in the stator. Now, in the stator, the magnetic field is always rotating. Now you have a rotor inside it. So the rotor rotates as the magnetic field rotates. Okay. Now, if the rotor and the sorry, in the if the stator magnetic field and the rotor, if they two rotate at the same speed, then it is called synchronous motor. Okay. So the stator and the rotor, if they are rotating at the same speed, and I didn't say they're aligning to each other. I just said they're they're rotating at the same speed. Imagine you are on a highway. Okay, the speed limit on a highway is 75 miles per hour. So everyone travels at 75 miles per hour. Okay, but they're not next to each other. Okay, so Gomez or one person might be in front of me and I might be behind, but still we are at the same speed, 75 miles per hour. Okay, okay, that here it is the same. They two are rotating at the same speed, but they are not aligned with each other. Okay, that part most of us would get confused. So don't get confused. They're rotating like think of two vehicles on a highway. One is ahead, and the one is behind, but they are moving at a same speed. That that those motors are called synchronous motors. If the stator magnetic field and the rotor is rotating at same speed, then it is called a synchronous motors. In asynchronous motors, the speed is they're different. Stator and rotor, they're not moving at the same speed. Okay, so they are called asynchronous motor. In asynchronous motor, the best example we have is, what is the example? Induction motor. Okay, induction motor is an example of asynchronous motors. Okay, here stator and rotor are at two different speeds. Now coming to synchronous motors. Okay, we have permanent magnet synchronous motor, brushless DC motor. We have reluctance motor, switch reluctance motor. Okay, and there are few other motors also. As we go ahead, I will tell you those details. Now coming to synchronous motor. Okay, so we have permanent magnet synchronous motor and brushless DC motor. So when you take this brushless DC motor, why do you call? Why did Narendra, you are saying brushless DC and you are speaking it when you are speaking about AC motors? Why there is a contradiction? Okay, because the power supply is in a brushless DC motor. Okay, what they do is the power supply is DC, but but I'm saying, but in order that power supply is given to the state is split to the stator by using an inverter. Okay, and it acts like a AC motor. See, uh, for example, if you take any DC motors, so what we see, conductor and we see field. Okay, so a magnetic field and a conductor, that's the reason why they are rotating. Okay, uh, whereas when it comes to permanent magnet synchronous motor or a brushless DC motor. Okay, let me show you a picture. It is more easy like that. Just a second, guys. I want to show the right picture. There are so many here.
So sorry,
Yeah,
Navin,
yeah,
so
yeah.
what's the
Please,
typical
please.
voltage that is applied to a motor in a vehicle? For example, Tesla, you know,
Oh, okay. So,
is it
so
230 volts or is it higher or lower?
230.
I'm just
No, I
asking. So
think
I don't know, 400.
it depends from the manufacturer to manufacturer. Some vehicles they have battery of 800 volts. Some vehicles they have battery of 400 volts. So it is around 240 for some vehicles. For Tesla, I don't know exactly, but for some vehicles it is 240. The motor, the voltage rating of the motor.
Applied to the motor. Okay, so I know
Yes,
the batteries are like rated at 400 or 800 or somewhere there, but it'll be stepped
yeah.
down when it's applied to the motor.
When the batteries.
No, batteries are always, I mean, I think, they
Yes,
store energy
800.
at a higher voltage,
Yes,
but when
yes.
you apply to
Yeah,
the motor, it'll be lower.
motor. Yeah. We lower it. That's where that you remember Professor is speaking about buck and boost converter.
Yeah, yeah.
See. So what they do is they use buck and boost converters. For example, uh, wait, just a second. I want to show you a picture. Uh, so, CDC model predictive control CDC. Okay, just a second. I
Are they
want to
using
show
a
you a pic.
converters in a battery electric vehicle?
Yeah, they use a lot of converters. Like, okay, can you see my
Okay.
picture I'm
Yeah,
sharing?
yeah.
Okay, so see, for example, so this is your battery in the vehicle. Okay, now this battery in the vehicle, we need to for two purposes we need. One is to drive the motor, right? Another one is to power the remaining devices in the car, like the windows which need to move, the wiper which need to move, the microcontrollers which need to operate, okay, the CAN bus system, and many other air cooling I mean AC air conditioning, and also the heater. There are many other things, right? So if you take like this is an vehicle architecture, you can say, like in a block diagram. So electric vehicle you have, see here it comes DC to AC inverters and DC to DC converters. So in most vehicles we use AC motors, because in DC motor what happens is there are lot of parts which are touching each other. Okay, like the commutator and the brushes. If you take a look at a DC motor, okay, so what happens is in order to provide power supply. Oh, okay, here DC motor. There are a lot of touching parts in a DC motor. Like, look at this picture. See, so this is positive and negative. Here are the battery which are connected to the battery. So from the power supply, you give it to a brush. This blue and this blue are the brushes, and through the brushes you give it to commutator. This is a commutator. Okay, and this brown one is the conductor. Can you see it?
Yeah. I'm
Yeah.
aware of
So
this one.
so there so and these brushes and commutator, they're touching each other all the time. That's how they provide current to this conductor. Okay, now over the time what happens is they wear off. That's why whenever you see after 10 years or after like all the toys, after a couple of years, or if you take vacuum cleaners and all, after a couple of years the motor loses its it's the speed, or it's that amount of torque which is being developed. Like the toy which you played 5 years ago, when you try to move, it will move, but it will move very slowly, because the brushes and the commutator will wear off, and the amount of current which is flowing through the conductor will reduce, which in turn reduces the torque developed by the motor.
Yes.
Okay, so this is a major disadvantage when it comes to a DC motor.
So is
Whereas in
all
AC,
those the home
DC
appliances,
motors,
they are all DC motors, brushed DC motors.
mostly, yes, because they're very easy, very simple, and you can minimize the size to the, see, you have seen, see, so small. Okay, whereas AC motors, if you find there are minimum of this size, can't find small AC motors.
They don't use the AC motors in like a vacuum cleaners in like uh,
Definitely in toys, they don't use AC motors. In vacuum
okay,
cleaner also, I'm sure they're using some DC motor.
DC motor.
Okay,
Okay,
yeah, because they're very simple to build mainly.
they don't have to
Okay,
convert from AC to DC and all that.
is yeah. So because this wear and tear will happen, and the amount of torque developed by the DC motors is comparatively less compared to AC motors. So 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 they we prefer AC motors in the vehicles. Now coming back to your question, now now there's an AC motor connected here. Okay, so now what they do, so electric vehicle is either 400 volts or 800 volts depending upon the vehicle which you're using. Now now to provide power supply to the remaining components of the vehicle, we use these converters, DC converters. Okay, step down DC converter is a buck converter. Okay, and in the same way, to provide power supply to the to provide power supply to your motor, what we do is DC to AC inverter. DC to AC converter is called as inverter. Another example of DC to AC inverter is, for example, if you have solar panels at your home, the solar panels, your home will charge the battery in your home. Okay. Now, when you don't when you need power supply from the battery to your home, what you do, you remember there is another box. Okay. The battery will be connected to that, and from there the power supply will be provided to your home. That box is nothing but an inverter, which converts DC power supply to an AC power supply. That's what the inverter does. Okay, in a brushless DC motor, okay, for in a yeah. So I think your question is clear, right? Here we
Yeah, yeah.
use step down converter. Okay, so this is called a buck converter. Okay, I think you remember the circuit diagram also. Yeah, here, if you see here, okay, this is a buck converter. So in buck converter, what happens if you provide 400 volts, you can step it down to 220 or 240. Okay, but you can't go it to 12 directly. There are some limitations. It comes under a different subject, power electronics. But professor gave you an understanding of how these things work, right? So just understand. Oh, there is a converter here. Okay, building these is another subject. Okay, we'll discuss when you are going through that subject. Okay, so this is the buck converter, and in the same way, in order to charge your battery, okay, again, the power supply provided at your home is not again 400 volts or 800 volts. Okay, so what we do step up converter, that is called boost converter. Okay, we'll provide the AC is converted to DC using a rectifier, and that rectifier output is provided to a DC to DC step up converter, and this will charge the battery. Okay, here it is boost, here it is buck. Okay, guys,
Yeah,
shall we go
thank you.
ahead?
Thanks, Narendra.
Yeah. Yeah.
Yep.
Now, going back to our brushless
Sorry,
DC
so,
motor.
sorry, no,
Yes,
yeah, so sorry,
yeah,
Narendra.
please.
So just one question regarding the image that you were sharing. Why do
Okay.
we have two external source is directly linked to the battery.
Right. This one,
Yeah. Both are AC, right? So we have to do AC to DC. But why do we have
rectification.
two sources?
There are two different like off-board, like uh, for example, in order to charge your battery, uh, see, wait, let me frame my sentence. See, these are these two are charging points. Okay, though these two doesn't represent one vehicle. Okay, this red is another vehicle, and if you have this blue one, it will be another vehicle. Here, uh, for example, if you want to charge your battery of your electric vehicle using the power supply at your home, then the topology will be the one in the red, the AC
Okay,
power
so
source,
it's a
AC
vehicle to
source,
grid, a grid to vehicle.
yeah, vehicle to, no, power supply at your home to rectifier, and so these two parts in the, these two components will be in your vehicle. Okay, in some
Okay,
cases. Here in this scenario, these two will be in your power supply board, like the charging
the wall
station.
box. Okay, like the
Yes,
wall box. Okay.
like the wall
Is it
box.
a
Yeah, you are right.
is it like a supercharger to a regular charger?
I think this is some
Supercharger, comes with a higher
higher,
uh,
yeah, and also
voltage and yeah.
I don't know the exact name. There is like stage two or level two
No,
chargers.
yeah, superchargers. They
So
charge
yeah,
faster,
those,
right?
yeah, I think those vehicles have this inbuilt inbuilt electronic
Converters.
circuit where, yeah, converters and also the rectifier, which will directly charge your battery. Whereas the other ones, you need
So
to, in the
home,
vehicle you'll have a system. In this system is in your vehicle. Here this system is in the charging station. That is the major difference. That's it.
the
But
110
if
will
you,
be like a home network.
yes,
And then
home
400
network,
is
yeah,
like a professional charging station.
charging station, yeah. But if you, one thing you need to remember is either you are using your home or you are using your onboard circuits of your vehicle, the conversion is the same. Always you need to take the AC power supply, convert AC to DC using rectifier, and that DC again you need to level up or boost it to the level of your battery in order to charge your battery. After boosting it, again, if you want the vehicle to run, you need to step down it to provide it to the sources in your to provide it to the other components in your vehicle, and also you need to convert it DC to AC to give it to your motor. Okay, so that's all about converters. That is your question. Now coming back to our topic of brushless DC motor. So this is an example of a brushless DC motor. See, here in a brushless DC motor, so what do I do is I take DC power supply. In a permanent magnet synchronous motor, I'll take AC power supply directly. Whereas in a brushless DC motor, I'm taking a DC power supply. Okay. And by using an inverter, I'm converting it into three voltages, VA, VB, and VC, and providing it to my motor. So, so, so So here, see, in a AC motor, again there are three phases, VA, VB, VC. Okay, whereas in a DC motor, you provide DC power supply and you provide the magnetic field. Here, the both things are the both the things are combined in a brushless DC motor. I am taking DC, but by using an inverter, I'm converting it into AC. Okay, so and like in the DC motor, there are no contact parts. In a brushless DC, again, the rotor is rotating because of magnetic attraction and repulsion. Okay, so so it is it's the acts. it is working on the principle of AC motor, but the power supply which you're providing is DC. That's why called brushless DC. In a DC, there are
Sorry,
brushes. Yeah, yeah.
sorry, Narendra.
Yes.
So I understand the low power battery provides up, and I think it allows the manual control, the control for the motor. So the high
Yes.
power battery basically supplies power to the motor itself. Right?
Yes.
Okay. So
Yes.
how does yeah, DC motor, the DC no no say how does that high power battery supplies a three-phase power?
Oh, the circuit is called inverter. This one, inverter circuit. See, uh, we we don't have circuit in our class, but it is really simple. Okay. Now imagine this is a DC power supply, right? So
Yeah.
yeah, this is DC power supply, and these are MOSFETs or any switches which you think of. Okay, so now when you studied electronics, you might have understood how these MOSFETs work. So example, like let's just I'm revising the topic. Imagine there is a pipe. Okay, this pipe has a valve. Okay, now imagine this is your MOSFET. Okay, now this is how a MOSFET works. So so the water is nothing but your current which is flowing through the MOSFET. Now this is the voltage or the PWM signal which you provide at the gate. Now if you open the gate completely, the total water will flow through the opposite side, right?
So it's like a dam control, right?
Yeah, not yeah, dam control or a valve, any kind of pipe
Yeah.
which has a valve. Okay, now if you open it half, there's only half amount of water will flow through, right? So the amount of water which is flowing through the other side can be controlled by using this valve. Okay, in the same way, what we do in the inverters also is switching. We control the switching of these MOSFETs. Okay, you are providing DC power supply here. Okay, and that voltage appears here. Okay, that voltage appears here. Okay, here. Now, now what we do, we by these switches S1, S2, S1, S2, S3, S4, S5, S6, they are given to a microcontroller.
Okay, okay, got it. Okay.
Okay,
So,
so I so this microcontroller is connected to a small power supply, like a low power battery, like 12 volts battery. All you need is 12 volts, right, for a microcontroller. And you have a program here to control the switching of these
MOSFETs.
switches, of these MOSFETs. Okay. Now, whenever you control the switching, you what you do, so then you know you have a control on the flow of current inside this circuit. Now let's take a small example, S1 and S4. This is S1 and this is S4. Okay, this is three phase, but we're I'm only doing it for one phase. So S1 and S4, you know how to do it. So the amount of current can be controlled by the PWM signal you provide to this switches S1 and S4. So initially you'll open it for a small time. So there will be small amount of current. Again, you'll open it, again, you will increase the PWM duty cycle, increase it, increase it, increase it, increase it. Again, you'll reduce it, reduce it, reduce it, reduce it. Then again, what you'll do, you will change the direction. Like initially, imagine imagine the current is flowing in this direction. Okay, uh, yeah, here like this. You keep changing the, because this technique is called SVM. Okay, they use a technique called SVM in order to convert AC DC to AC. It is SVM. voltage modulation. Switched voltage modulation is the name. So then again they change the direction of the current by again taking another switch into consideration. Again they'll will get this AC current from this DC. By controlling the switches how they are opened and closed, we get this AC current. This AC which we got from the inverter, okay, which we got from the inverter is provided to the this motor.
It's a three phase. So it's a single
Yeah, three
phase.
phase.
Yeah, single
Yeah.
phase DC power from the battery is
No,
converted
no.
to a three phase.
There is no phase in DC. It is just a DC.
Yeah, it's only DC, but this switching transistor basically converts that into like a
Three
phased
phase
input, three
AC.
phased input. Okay,
And
three
yes, three
phased
phase
input.
AC. Yeah, three phase AC. And we give it to the brushless DC motor.
Okay,
Okay. So, but
but
whereas in a
that
permanent
brushless DC motor, even though the name up is a DC motor,
DC
it
motor,
it takes the AC.
yes, it takes the AC. But we are providing DC power supply. That's why we don't call
Okay,
it as AC motor anymore. We call it as
okay,
a DC motor. The input is DC. We kept in the category of AC motors and we call it as brushless DC motor. Because
okay, okay,
in a DC motor, there should be brushes, but there are no brushes here.
okay. Got it.
Okay, there are no touching parts. There are no contacting points. Okay,
Same
guys.
RMF, right? Same RMF in a
Yeah,
DC motor, brushless DC motor. The, it's a
same RF.
rotating magnetic
Yeah,
field.
yes, rotating
Okay.
magnetic field.
Field
Yeah,
that basically, yeah. So
yeah,
we just lose the commutator.
and brushes also.
So basically, like without uh, with brush, if it's a DC motor, it's a DC motor. If it's a brushless DC motors, then actually, how do you define that actually with respect to the
There are
brush? I mean, only
there are no brushes.
DC. No, there's no brushes.
There is no brushes.
Okay,
There
got
are
it.
no brushes at all.
So
There are
we
no
we
brushes. There are no commutator.
so the field is in a brushed DC motor. The field is applied to the armature, or I mean rotor, and in a brushless DC motor, the field is applied to the stator, right?
The field is supplied. What do you mean by field here?
Yeah, because through the commutator, you supply power to the rotor
Yeah.
in a
See
brushed DC motor.
the wording is, we should be careful about wording when it comes to these motors. Okay, when it comes to DC motor, you can use the words armature, okay, and field. Okay,
Yeah,
when it
right.
comes to AC, you should have to use words stator and rotor. You can't bring this word here. Okay,
I'm only
so
talking about brushed DC motor and brushless DC motor.
oh,
Isn't the
breast
field?
DC.
Yeah,
Okay, breast
yeah,
DC motor and
and
breastless
brushless
DC
DC
motor.
motor. The
Oh,
field is reversed,
okay.
right? The field is
The field
reversed.
is no. Like think. See, in a so there is no breast DC motor. There is only DC motor. The usual convention is DC motor. In
Okay,
a DC motor, there is a brush and there is a commutator. Okay, in a brushless DC motor, there is no need to talk about brushes. There is no need to talk about field,
commutator.
anything. The commutator. There is only two things: stator, rotor, inverter, and DC power supply.
Okay, okay,
Okay, so
okay.
so okay. So when I say brushless DC motor, just imagine it's an AC motor. That's it.
Yeah,
Because
yeah.
the
The
the the,
principle of
the work
working is similar to
similar to,
AC
yes,
synchronous motor.
yes, AC synchronous motor. Yeah, you're
Okay.
right. Okay. Now, now, guys, any questions? Shall I continue? Ayub, uh, Tofik,
I'm
hello.
good. I'm
Good,
good.
thank you, guys. What about others? Buckley,
Hello. Yeah, I'm hearing well. Yeah. So basically, to summarize that, the brushless it is an AC asynchronous, right? This is the key here.
Yes,
For
yeah, you're right. That's the
but
key.
there is a confusion here from that point. Yeah, why we call it DC?
Yeah, why we call it this?
Yeah.
Yeah, I hope it is clear now. I hope it is clear
Right.
now.
Yeah.
Like,
Okay.
shall I go ahead?
It's because
Yeah.
of the input, right? The input is DC.
Yeah,
That's the
input
reason
is
Right.
why it's
DC.
DC. Even though it
Uh,
converts it itself.
The input is A3 phase, right?
No.
Yeah, see. Yeah. Here input is three phase, but basically you need an inverter and you need a power supply. You're taking
The
battery.
DC
See again, if you
converter.
you're giving it an inverter, and then you're
Yep.
providing it to the motor. So
Right.
you can think of this as an input, or you can think of this as an input.
Okay.
Okay, if you think of this as an input, then you're saying, oh, again, I'm providing three phase. That's why you call it, that's why it is in the category of AC motors. If you think
Right.
of this as an input, that's why we call it as brushless DC motor.
Right. I gotcha. Okay.
Yeah. And these are most commonly used motors in the drones. And I can show you
Oh.
tomorrow. Right now, I don't have, I don't, I didn't bring, I don't have the equipment at my home, but I can show you tomorrow the complete setup. Okay. Now, coming back to our topic. Okay, field oriented control of this brushless DC motor. Now, the torque developed by these brushless DC motors is given by this equation. Okay, magnetic field R, L, and sine of theta S minus theta R, ns by 2. Now, imagine you have built your motor, a brushless DC motor. Now, after building your motor, if you observe, okay, once the motor is built, okay, everything in this are staying the same, like they are constants. Okay, there is current also. Sorry, the important factor, current through the stator. Now, if you take this equation, okay, once the motor is built, okay, if the motor is built, then if you have a fixed power supply, everything in this are constant except two things, that is sine theta S minus theta R, and is the current which you are providing to the stator. Now, so torque is directly proportional to the sine of theta S minus theta R into is. Is is the current which you are providing. Okay, current, there is always, like, it depends on you. Okay, if you increase the if you increase the, I mean, if you want to increase the torque, you can increase the current. What is the other way to increase the torque? Now imagine if there is a sine function. Okay, if there is a sine function, so the sine, so depending upon the angle between the theta s minus theta r, the torque is varying, right? Imagine if theta s minus theta r is equal to 90 degrees. Or imagine if theta s minus theta r equal to 0 degrees. What is the torque? Guys, if theta s minus theta r, angle between the stator and angle between the
So
rotor is 90 degrees.
yeah, when it
So
is
then
zero, it is zero.
when it
Torque
is
is zero.
0, when it is 90, it is maximum. When it is 0, it is minimum. Okay, so when it is 90, the torque developed by this brushless DC motor is maximum. So if you can find a way to keep the angle between the stator and the rotor to 90 degrees, then with the same motor, you can actually get maximum torque all the time, right? So
Mhm.
here, this topic, that's why it is called field oriented control of brushless DC motor. The concept completely speaks about how to make the, the angle between the stator and the rotor 90 degrees. Okay,
Sorry,
today's topic.
Narendra. So sorry, Narendra. So we apply the the power to the stator, and we have a rotating magnetic field. Now
Yes.
on the rotor, um, we have a permanent magnet, or do we have a yeah, electromagnet on a brushless DC motor?
Oh,
Or we
on
have
the
Yeah, on the rotor,
permanent magnet.
permanent magnet.
Yeah. See, again, sometimes they use, mostly it is permanent magnet, you can say.
Okay, okay. So
Okay.
so that angle,
Angle between the
the two
resultant,
fields
say,
have to be
yeah, twist, yeah, resultant fields. Okay. So now, okay, I'll go in detail, Guna. Now just understand the logic here. Okay. Now see, how do you get the maximum torque out of this motor? Okay. So either by increasing the current. Imagine you built the motor either by increasing the current or by controlling the angle between the stator and the rotor. Now, if the angle between the stator and rotor, if you can make it 90 degrees, then you can obtain maximum torque out of it. If the angle between them is zero, then you'll get the minimum torque out of it. So in field-oriented control, what this topic is, field-oriented control of a brushless DC motor, what my aim is to make the angle between the stator and the rotor as 90 degrees. Okay,
clear,
that is my
Narendra.
aim.
Yeah,
Yeah.
clear. So
So
what are the other
how
terms
do
that are there?
oh, this is the torque equation.
No, yeah, I got it. That B R L N S,
Okay, so
is it a
L
pi
is
or?
the no ns into pi.
Okay. What are
So
those parameters? I mean, sorry, I didn't get that.
oh, you didn't go through the derivation of the
Restless DC motor, I don't think we
no
went
that
to that.
no the derivation is the same for permanent magnet synchronous motor and brushless DC
No, we
motor.
did not go through any derivation.
Oh, oh, okay. Okay, just give me a second, then I'll open a different one and I'll just go through quick derivation. Okay, just a second, let me open this one
Yeah,
so that
sure, sure. No
I will
problem.
explain the terms and how they came. Okay, guys, anyhow, it is 5. Let's take 5 minutes break and then we'll come back and then we'll start from here how to make theta s minus theta r 90 degrees and what are the how do we do that? Okay, now the time
Okay.
is 4:56. We'll get back by 5:01 and we'll continue.
Okay.
Okay.
Thank you.
Okay.
Thank you.
Thanks.
Guys, are you back?
Yep, we are.
Yeah.
I'm listening.
Okay. Okay. So coming back to that equation. So now, so there are couple of terms in that. Okay. B. Okay. R. L. Okay. Sine theta s minus theta r ns by 2 into pi into I. So coming, so again, uh, getting back one step ahead, how the rotating magnetic field is developed in a stator of any kind of AC motor. So to develop that rotating magnetic field, okay, Nikola Tesla is the one who came up with this sinusoidal kind of winding. Like when if you have opened any motor, what you generally see, you see a lot of coils, copper wires, which are being wound like this, right? See, this is what you see when you open, right? Guys, are you with me?
Yeah. Yep.
Yep.
Yeah, this is what you see when when you open any kind of motor, whether it's an AC motor or a DC motor. Now we might think that these windings are done in a random fashion, but they're not. In order to get that rotating magnetic field, the windings are done in a way, in a sinusoidal fashion, you can say. See here, the the number of windings in each of these slots, in general, in an AC motor there are more slots than what it is shown in this picture. Okay, here for the liberty of a picture, the number of slots were reduced, but there will be many slots. Like in each slot, if you see, the windings are being increasing. Check the red one. Like check this phase A. In the first slot there is only one wire. In the second slot, two, three, four. So they are in a sinusoidal fashion. In the same way, even for the phase 2, okay, they are in sinusoidal fashion. In the phase 3, they are in sinusoidal fashion. So because of this particular kind of winding which they made in the stator of the AC motor, what we get is a rotating magnetic field.
Sorry,
Okay,
Narendra. Uh,
okay,
so in the illustration, you have three
okay,
windings, right?
okay,
And
yes.
they seem to be like um, equal set of windings. It is not
Yeah,
in a.
yeah, yeah. They didn't show in this picture, but actual windings are done in this manner. Okay, so
So that's only
because of
one. So that'll be like probably at the least number of winding. So the outermost slot, you have only one,
yes,
and then you have
yeah,
like
yeah,
two, and it goes like that, right?
yeah, yeah, yeah. I mean, just don't take it as one. It might be more. I never built a motor, but I know that the windings are made in a sinusoidal fashion.
How
Good.
how do they
Did you?
achieve it? Is there any specific way they go, or is it like a
Uh,
random?
no, no, not random. There is a math behind it. See, see. Uh, if ns into sine theta, okay, so ns is the total number of windings, number of turns in winding. Like imagine at the maximum you need like 100 or five. Imagine you need 500. Okay, then the way it is done is in this way: ns by 2 sine theta. If the angle is less, then the windings are reducing. If the angle is, if sine theta is 90, then it is ns by 2. And if the sine theta is again 0 to pi, you know how the sine wave is changing, right? So
So what
that's
is
how the
the
winding.
okay? The capital NS is the number of turns in a winding,
Yes,
and small NS
winding.
is what?
The resultant.
The resultant of the field.
No, 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 no. Just the resultant windings. How many you are actually doing it? See, uh, imagine the total number of windings are the see, number of turns in a winding. Like at the peak, imagine here at the peak, imagine there are 500 windings.
Okay.
Okay. Now you need to keep reducing on the opposite side.
Okay.
So, okay. Now how do you know what are those windings by using this formula?
Winding trick, sinusoidal distribution. Okay.
Yes. So imagine there are 500. Okay, 500 into imagine you are at an angle of 30 degrees.
Okay.
This
That's
is the number of
250.
windings in. Yeah,
That's 250.
250 into sin. Yeah, 250. Sine 30. How much it is? 1 by
As
2.
a half.
Half. Yeah. So the winding should be like they might take a different value, which is which is equally divided. Okay, then you should do around 125 windings for that slot.
Okay. Okay. Got it.
Okay, the slot angle is changing, right, every time. When you are at maximum, then you do the maximum 500 windings, and you keep repeating it.
Okay.
Okay, so this is only the resultant winding. That is the formula. So that's how they do the winding for each phase. Because of this winding, whenever you provide an three-phase power supply, you will get a resultant magnetic field which is varying. Because because see, mm, because the current. Okay, I don't want to. Okay, so okay, let us see. So so now ns, the number of windings is given by ns by 2 into sine theta. So ns by 2 into sine theta is the ns by 2 into sine theta uh, is the number of windings. Now from the number of windings you can find the field amount of magnetic force, magnetic field, or the flux which is magnetic force which is developed, which is given by ns by 2 into amount of current. Integral is converted into cos theta.
So the capital F is the field, the stator
Yes,
field.
magnetic motive force.
Okay.
Okay, so guys, I'm not gonna go through the derivation. It's already done. So I'm just trying to explain you. If
Yeah.
not,
Yeah. Got it. Got it.
okay, so if not, if you still want a derivation, we'll do it tomorrow. Okay, for today, I'm just trying to explain the terms which are used in the torque equation. Okay, my aim is different for today.
Got it.
Okay,
Got it.
but
Got it.
yeah, okay. Now you got the magnetic motive force. Okay, which is integral. We are finding integral because this is at one particular moment. Later you want to integrate it for whole from zero to for the whole slotting. Okay, for the whole slot from 0 to 180 degrees. Okay, once you do that, once you find the magnetic motive force, then you can find the magnetic flux, which is B, which is given by ns by 2. Okay, L is the length, ia into cos theta. Again, this is the magnetic force. Now once you know the magnetic flux, after finding the magnetic flux, okay, magnetic motive force for each of the terms is different for each of the phase. This is phase A, phase B, and phase C. There are three phases. Okay, one, two, three. Each phase is 180 degrees, 120 degrees apart from each other, and each phase by itself are in the are in a fashion or in a or the windings are done in a sinusoidal way. Okay, you need to remember that. Okay, so these equations, they represent that. Okay, each phases and the magnetic motive force developed in the each phase. Now the torque is nothing but here. Professor has gone through all of these again. Now, yeah, here the torque equation. Wait. Why I came to this one? Oh God. Where is the torque equation? Okay, here. Maybe I can show it here. Yeah. See, now So there are three windings. Okay, NS A, phase B, and phase C. Each of these phases are 120 degrees apart from each other, but the windings are ns by 2 sine theta, ns by 2 sine theta, ns by 2 sine theta. Now, if you take the magnetic field developed, magnetic motive force developed, it is given by BLI. L is the length of the rotor. Now the torque is given by F into R. Okay, force into R. Here the force is nothing but BLI. BIL. I is the current, L is the length, P is the magnetic flux, R is the distance between that stator and the rotor. There's a small gap between them. Okay, now here, okay, here what here if you see, okay, the magnetic force developed, okay, I substituted this equation, ns by 2 sine of theta r plus zeta minus theta p into this, and I did the integration for 0 to 2 pi to find out the total torque developed by the uh, yeah, wait, let me make it more clear. I don't want to confuse you. Wait. Just a second, guys.
Okay.
There it is still
So,
confusing.
so the torque is basically force into rotation, right?
Yes,
Force into
torque.
rotation, and
Yeah,
then force is magnetic,
force,
yeah, BIL.
motive force. Yes.
Yeah, so total magnetic magnetometric. I'm sorry, magnetic
Yeah,
force.
you're right. Yes.
Okay. What's the I? You said I is the gap between the rotor and the stator. You said.
No, I is the current,
Oh,
resultant
I is
current.
the time.
I
Oh, okay,
because
okay.
the so force is BIL. Okay. B is the magnetic flux. I is the current. L is the length of the rotor.
Length of the lines or um, the winding,
Yeah. How far?
the
How far?
winding length.
Yes, the winding length. How far it is wound. Okay. Now here. Okay. BIL. Okay. Guys, I'll go through the derivation tomorrow. Let's continue today. I'll make it clear. Now I don't
Okay.
want to bring it to confusion.
Yeah.
The whole derivation takes one hour class. Okay, I'll go through it tomorrow, explaining each of these details, how we got to that conclusion. Okay, today let's finish this. Then tomorrow I'm sure I'll start with that. Okay. Now
Okay.
today let's go with this one. Okay. Now BRL sine theta s minus theta r, where my aim is to make angle difference distance, or you can say angle between theta s minus theta r is 90 degrees. So 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 that I can achieve the maximum torque out of the motor, out of the motor which is built. So to do that, how to do that? To achieve that, I'm gonna employ a technique in mathematics called Park transformation. So, so what is Park transformation? How it is been implemented? Now, for example, if you take this is x-axis and this is y-axis, okay. Imagine there is a line called A, okay, which is making an angle theta with x-axis. Now, what do you do if you want to find out the projections of this line A on x-axis and y-axis? Okay, then what do you say this? We
A
call
cos
this
theta,
as
A
A
sin
cos
theta,
theta,
A
A
sin
cos
theta.
theta, and A sin theta. These are the projections of this line A on this x-axis and y-axis. This same concept we will implement when if you want to achieve an angle between theta s minus theta r as 90 degrees. Now, for example, okay, now take theta s and theta r into consideration, and let us see how to make the torque 90. Now, now So there is an inverter. Okay, inverter. To this inverter, I'm providing battery power supply. Okay. Now from the inverter, the output is VA, VB, and VC. Or V alpha, V beta, VA, VB, VC at the three-phase voltages. These three-phase voltages, I'm providing it to the brushless DC motor. In the brushless DC motor, there are three windings, right? Guys, are you with me?
Yep.
Mhm. Yeah.
So there are three windings. These three windings produce the stator magnetic field. Okay, so here there are three currents: IA, IB, and IC. Okay, IA, IB, and IC are the three currents. But every time, okay, every time, so IA, IB, and IC. So with IA, IB, and IC, we'll have a resultant magnetic field which is called IS. I hope professor has spoke about it. Okay, which is called IS. IS is because what we do is if you take IA, IB, sorry, IB and IC, okay, we get IS by using something called Clark transformation. What they do is they take IA, okay, IB and IC by using Clark transformation. We convert them into I alpha and I beta. From I alpha and I beta, you have IS, right? Guys, are
What
you
is
with
I
me?
alpha and I beta?
Oh, okay. Professor didn't speak about this.
No.
We went over Kirchhoff's law, right? The summation. Right?
Yeah. Is it Kirchhoff law you're talking?
No. This is not Kirchhoff's law. This is Clark transformation.
No, we didn't go that far. Yeah.
You didn't go that far.
No,
Oh.
just summation, and output input.
Okay.
Kirchhoff's law. Lewis law.
Okay. Oh, okay. I have to go way behind.
I alpha is between like two currents and the other two set of
Yes, two
currents.
currents.
Okay.
Other two set of currents. Wait, no, not other two set of currents. What they call is Clark transformation. Oh God. Okay. Okay. Now, yeah, here comes the space vector. Now, okay, imagine you have three windings, right? Three phase windings, and because of three windings, you have three currents called I alpha, IA, IB, and IC, right, guys?
Yep.
Okay,
Yep.
I so IA, IB, and IC are the three currents which are flowing through the stator winding of your brushless DC motor. Now, now when I say resultant magnetic field, see, imagine imagine there are three currents going through three different coils. Okay, the three currents are out of phase. They are not in the same phase, right? So one is like this. Uh, Another one is 120 degrees, another one is 240 degrees. So another one is like this. All of them are out of phase. Okay, 120 degrees apart from each other. There is a phase difference of 120 degrees apart from each other. Now, at any given moment of time, if you consider, okay, there is only one current which is dominant. Okay, the other currents are not dominant because they are out of phase. Okay, that's a simple thing we can understand. Okay, for example, if you take here, then the blue is dominant here, the remaining two are not. Whereas if you take here, this phase 2 is dominant, here phase 3 is dominant. Okay, if you take here, there are three different phases. So at each phase there will be the one phase will be dominant and other phases will act on that, but they are not dominant. And okay, now because of these three phases, you'll have three magnetic fields. Do you agree with me?
Yeah.
Yep.
There are three coils. Okay,
Right.
there are three coils and there are three currents flowing through all these three coils. So all these three, when the three currents flow to three coils, there are three magnetic fields developed. But the amplitude of that magnetic field at that moment will determine which is a dominant magnetic field. So if you observe this diagram, there is a current called I alpha, I beta, or I gamma, or you can call it as IA, IB, and IC. So here there are three currents. Okay, IA, IB, okay, IC, IA, IB, and IC. These three currents, IA and IB and IC, the they produce one magnetic field, a resultant magnetic field, which is called as, that is known as IS. This is called as IS. How do you find this IS is very important. That is what the angle of the stator. Okay, angle of the stator. Now, now to how do you find this IS or the resultant current, and which is the reason for the resultant magnetic field? How do you do that? By using a technique called Clark transformation.
So whenever there
Clark.
is some magnetic field that comes into being,
Uh-huh.
does the magnetic fields they have interference and diffraction and all of that, or like
I'm
do
not.
they
I'm not
do
getting
the
your question.
magnetic field have do they when they are
uh,
applied when they're
you're
applied at the
talking
same
about
phase they will amplify, and if they are opposite they'll kind of
uh, they'll get rid of the other
yeah,
one. That's what you're speaking
yeah,
about. So
yeah.
yeah. So all these three. Okay. I'm not sure about magnetic, like electromagnetics, which is happening in there. But I can uh, I'm not sure about
Because I mean,
like,
if you look at the magnetic field that is
yeah. I
on a
understand
wire,
what you meant. Yeah, yeah,
yeah,
yeah.
on a wire
So
it is round, but then if you have a
yes,
coil, that's completely different, right? They
yes.
interact and
It
they change.
change. Yeah. Here I don't know to that level of magnetic how the magnetic field are what you say
Combining together
combining, or
or
no,
just
not
trying.
sure. Yeah.
Okay,
I think it comes under electromagnetic field subject. No idea about that.
okay,
Sorry,
okay,
Guna.
no problem.
Yeah.
No worry.
Now, now, guys, get back to our topic. So there are three currents, and the three currents produce three magnetic fields. Or you can say from IA and IB and IC, we can find the resultant current called IS. Okay, what is this IS, or this IS is the one responsible for the for the stator magnetic field. Stator magnetic field. Okay, so what it is happening? We take this IA and IB and IC. By using Clark transformation technique, we found I alpha and I beta. How it is done? So if you take, yeah, if you take IA, IB, and IC, and if you multiply with this Clark transformation matrix, then you can find IS or I alpha or I beta. Okay, this IS is in the direction in which the resultant magnetic field is developed. when you have three currents, okay, when you have three currents, the resultant field is IS. That IS is dependent on I alpha and I beta. How do you find this I alpha and I beta? By multiplying this IA, IB, and IC with this matrix called Clark transformation matrix. How it is here? See, IA is multiplied by 1 and 0. IB is with minus 0.5, 0.866. IC into minus 0.5 and minus 0.866. Once you multiply that, you will have I alpha and I beta. I alpha and I beta will determine the resultant magnetic field of this rotor. I have a small MATLAB which shows the same. Okay, let me run that for you. Okay, I don't think we will finish our topic today. AC main, stator winding. Three-phase stator. Oh God, we are going back. Okay, guys. Just a second. It is taking a little bit time. I want to show you the resultant magnetic field animation so that you'll get a better idea. Okay. Can you guys see the animation?
Yep.
Yeah.
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 See. So here there are three windings. Okay. So one is blue, yellow, and pink. Okay, magenta. Now as the see at there are three phase, the three are 180 degrees apart from each other. Now, as you move on the time, the amplitude of one phase will be dominant at one time, right? So as you move, like if you observe this sinusoidal waveform, like you'll have a continuation, right? Okay, so these sinusoidal waveforms will develop the magnetic fields. From that magnetic field, the resultant field, which is developed by the stator, is nothing but this white line, which is showing as North Pole and the South Pole. Run one more time. Yeah. So three phases, okay, will result in one particular resultant field. Okay, that is known as IS. We represent as IS or I alpha and I beta.
So basically,
The
this
white line
represents
is the
the rotor, right?
NS.
Yeah, the white line is the
NS.
resultant magnetic field because of those three phase currents which are flowing through the stator of the brushless DC motor.
Got it. Thanks.
Okay,
Sorry
so
to frequently
sorry.
ask some question.
No, just I mean this resultant basically represents the torque on the shaft, if you want to consider the
No,
rotation. No,
no. It is only stator stator resultant field.
but then the net result that goes into rotation, right?
So no. Here you're confused. See.
Oh, okay.
So here in the motor there are two parts,
Mhm.
stator and the rotor. Okay. So
Right.
the rotor is a magnet. Okay. When will this magnet move? When there is an attraction or a repulsion force acting upon it, right?
Mhm.
The rotor will not rotate by itself.
Right.
It
Okay.
will stay like that. Okay. When will it will rotate? When there is an attraction or when there is a repulsion force acting upon it. Okay.
Mhm.
That attraction and the repulsion force should be developed by the stator, which is stationary.
I see. So basically, this white line here basically affects the rotor rotation, right?
Yes, this white line affects the rotor rotation. Yeah, you are right.
Right. This is what
I
I
have
meant.
another.
Yeah. Yeah.
I have another picture to show it to you. Yes, here.
Yeah. So the end
Okay.
result of this basically is the rotation.
Yes. See here. This is a magnet. If you can see inside. Okay.
Mhm.
This 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 is this thing. This is not a three phase. This is just like for a better understanding. I'm saying. Okay. Now this magnet. This is the magnet. Okay. It won't rotate by itself unless this is the stator. These three are the stators.
Right.
This one. These are the stators. Okay. This is the stator. Okay. To this stator, you will connect the inverter.
Mhm.
Inverter. This inverter will provide voltages VA, VB, and VC. Okay.
Okay.
Now this VA, VB, and VC. This is a simple illustration, but just to give you an idea of what happening. Now here if you see what happening, there are only two magnets or two stators are active at a time. Okay, one
Yeah.
one is not active here. This is not active here. This is not active. Okay, now because of these two, okay, or at any given moment of time, you can say at any given moment of time, you can say, yeah, say take this picture or for better understanding. Okay, so yeah, take this picture here. The C is not active, whereas A and B are active. Okay, the current is flowing through. This is A. Okay, this is A, and this is B. Can you see?
Yeah.
Okay, so A and B are active. So here the current is flowing through the A and B. As the current flows, and in the C also there is a current flowing. I don't mean there is no current flow, but it is not high in magnitude to attract the rotor. Now, now A and in the current is flowing through A and B. And the rotor in this type of motor, the rotor is on the outer side. Okay, this is called outrunner brushless DC motor. Okay, the picture here at the starting I showed is in-runner brushless DC motor.
Uh-huh.
Okay, that
Yeah.
okay.
Different
Now
type. Yeah.
what happened? Yeah, different types. Now the permanent magnet on the outer side or on the rotor, there is a north pole here and there is a south pole here. Now what happens when the current is flowing through this coil? The coil will be converted into an electromagnet. Now this electromagnet, the A, this pole is south pole, and the B, this pole is north pole. And and in the brushless DC motor, the outrunner or the rotor which is on the outside, it has north pole here and it has south pole here. So what will happen? these two north poles will repel each other, and this north pole and this south pole will attract each
Attract.
other, and this will move here.
I see.
Okay, now the rotor rotates. The black one is the rotor. Now the rotor rotates. Now again, what you will do then, if this is south pole, now you will change this to north pole. You'll change this to north pole once this n is here. This n will come here because of that
Right.
repulsion and attraction
Rotation, yeah.
forces. And again, you will change this to n again. Then again, there will be a repulsion force between the black and the metal piece, or you can say stator.
Right.
This is stator, and this is rotor. Then again because of the repulsion force, it will come here. Again, you'll come here. So what actually you're doing? You're actually controlling the current which is flowing through each of these coils. You understand?
Right. Right.
You're okay. You're actually controlling the current which is actually flowing through each of these coils. Now this is a simple, very simple example. Imagine if you take a brushless DC motor in a electric vehicle, you took it to application to a electric vehicle. Here you have only the three coils, or you have very this is a very simple explanation. But if you see, I'm only showing two magnetic fields, even though I know there are three coils, V alpha,
Three of
V
them,
beta.
yeah.
Yeah, there will be three of them. There will be three of them. There are three currents. Okay, sorry, currents. Three
But one would be
currents.
dominant, right? Yeah, the big one.
Yeah, IVA, IB, and IC. There are three currents. Okay, but there will be only one magnetic field. Output magnetic field will be only one. How it is happening is, from this IA and IB and IC, I can figure it out which one is dominant depending upon the diagram. This diagram. See here. Now it will be.
Right.
I hope this will be more clear.
Right. So there's a
Yeah.
dominant Clark transformation. Yeah.
Yes, because of the Clark transformation, what I will find is, from this IA and IB and IC, three currents which are flowing. Okay, I can find I alpha and I beta, or I can find IS. This is IS, resultant stator magnetic current. Okay, this is which is the reason, or which shows the most dominant one here, as Guna is asking, out of these three, when I apply the Clark transformation, I'll find out what is the main one. It might be like this: south pole and north pole. Okay, how do I find the resultant magnetic field? By using this Clark transformation technique. Clark is the one who came up with this one. Okay, how do I do that? From IA, IB, and IC, if I multiply Clark transformation, then I'll find I alpha and I beta. From I alpha and I beta, I can find IS.
Yes.
Okay, IS is the one. IS is the IS is the one which determines the direction, or which determines the resultant magnetic field of your stator. Okay, now
That's why
now
it's
now
called
stator.
IS, right? Yeah.
Yes, IS cap. Okay, because it is an vector, it changes, right? That's why it is IS cap. How that IS is, this simulation will had shown you what is that IS. This simulation is showing that IS, how the IS is changing. See,
So
this is
what
how
is the
IS is.
significance of this IS, Narendra? Is this a
How
theoretical one or is this the physical one?
Yeah, no, it's a theoretical one.
Okay.
Okay, it's a theoretical one, because all you have the in this the pract I mean in it the physical ones are the magenta, blue, and the yellow.
Right, right.
Okay. Okay. But out of those, because of those three, you have this white.
Okay. So
Okay.
theoretical
And
resultant.
please repeat.
Theoretical resultant, right?
Yes, theoretical resultant. But it is actually there. We can't actually even you can't even see the magnetic field, right? With your own eyes. You
Yeah, yeah,
just
yeah.
know
Mhm.
that there is a magnetic field. Okay. Now that we know that the stator magnetic field is varying. See, north pole and south pole of your stator are varying. See, because you're
Mhm.
providing AC sine wave. Okay. And because of the windings which you did, sinusoidal winding. Okay. Because of that sinusoidal winding which you did, you developed a magnetic field which is rotating. Now, inside this, the green, you can think of it as a rotor. Now, the rotor also is a magnet which keeps following this stator at the same speed, because this is called a synchronous motor. Both the stator and the rotor, they rotate at the same speed. Now, my aim in this class is to make the angle between the stator and the rotor 90 degrees, so that I can achieve the maximum torque when the rotor is
Mhm.
rotating. Okay, how to do that? How to do that is my main goal of this class. So for that, I for that I'm going through a mathematical approach. Okay, where I need to make the angle between them as 90. Okay,
Mhm.
so how do I do that? How do I make it 90 degrees? For example, or you can say, just for a small case of for example. Okay, so we know IS. IS is the stator magnetic field, IS, and it has a IS cap. Okay, IS is because of I alpha and I beta. Guys, do you agree? From here, from if you look at this, IA, IB, and IC, okay, are producing a resultant magnetic field IS, and intermediate you call it as I alpha and I beta,
Mhm.
right?
Right.
Yep.
So this is I alpha and this is I beta, and this is IS, and the angle is theta S.
Mhm.
Okay, and here in this one, you can think of there is something called IR, or or you call it as theta R, the rotor angle. The rotor is moving along with the stator. Okay, at any
Right.
given moment of time, I'm just imagining my rotor is here, which is making an angle of theta R. Okay, or you can call it as BR. Okay, uh, okay, resultant magnet. Oh no, I can't call it as B. Sorry. Okay, so this is your rotor. Now now what I should do? I need to make angle between these rotor and stator 90 degrees. So for that, what I will do is I will find the projections of IS on this theta R line. Okay, this is your rotor. Okay, this is rotor. So here, what did I do? I found projections of A on this x-axis and this y-axis, right, guys? And they are given by A
Mhm.
cos theta and A sin theta. Here, what I am doing is I am finding the projections of IS on this rotor. Okay, theoretically, I'm doing something. Okay, so those are called, sorry, yeah. So these are the projections of this IS on this rotor angle and on this. These are the called ID and IQ, direct and quadrature axis of your stator in the consideration of rotor or along the rotor.
Mhm.
Okay, now what is my aim? My aim is to make the angle between the rotor and the stator 90 degrees. Now, if I can push my IS to ID, then angle between the stator and rotor will be 90 degrees. Do you agree with me?
Right. Right.
Okay. So my aim is to, so I need to build a control system in order to make the, or in order to develop the maximum torque. How I should do it? I need to push my stator angle to the ID axis so that the rotor and the stator will be at 90 degrees to each other, developing maximum torque for the same motor which has been built. Again, see. Okay, guys, do you agree with this?
So for this, we know where the IS is.
For this, we know where the IS is because we know I alpha, I beta, I gamma.
Yes.
Okay. Okay, we know I alpha, I beta, I gamma. We know the amplitudes of I alpha, I beta, IA, IB, IC. From there, we can calculate I alpha and I beta. From there, we know what IS is and angle of the IS. Okay. Hello, guys,
So
are you
what?
with
Yeah.
me?
How do we find the rotor angle?
Rotor
What is
angle.
the rotor angle?
The rotor angle will keep a sensor inside the motor, but finding the rotor angle.
Oh, okay, got it.
Okay, we'll keep a sensor to find where the rotor is at a given time. Now, see, now this is what at a given moment of time. Okay, these are the angles between the rotor and the stator with respect to an axis. Okay, imaginary axis you are taking. You're thinking of, okay, stator is making an angle of theta s, rotor is making an angle of theta r. Okay, you are sure. Now just only in the mathematical point of view, I'm finding this projections of is on this rotor angle. Okay, how do I do that? In the same way here. Okay, and here. So I have two more axes here. One is in the direction of the rotor, another one is 90 degrees to this rotor. So
To the
this is
rotor. Yeah.
called ID and this is called IQ. ID and IQ are 90 degrees to each other. 90 degrees to each other. Now imagine if you can because you have a control on I alpha, IA, IB and IC. Okay, so if you can push your IS to ID, if you can push your IS to ID, what will happen? Now your rotor angle, which is your yellow, it will be 90 degrees to your stator. IS
Mhm.
measured is here. IS desired will be here. Desired. I didn't develop my control system yet. I'm just saying if I could push my IS to ID, okay, then the angle between the angle between the stator and rotor will be 90 degrees, which will give the maximum torque for the same motor which is built. This whole concept is called field oriented control of a brushless DC motor. Okay,
Mm.
I'm okay, I'm controlling the field, okay, of the of my brushless DC motor to develop the maximum torque. What technique I'm using for that? The technique is called park transformation.
Oh,
The
the
technique is
park
called,
does do that. Mm.
okay, here what does the park will do? Now we know IS, okay, uh, now what does the
Just a
park?
question on just a
Yes,
relative
please.
question on the
Yeah, please.
north-south magnet. How does it compare to the I rotor? So basically, to the 90 degrees. How would be that the south north poles will be?
No. Can you please ask again? Sorry, I didn't
Oh,
get
okay.
the question.
For example, the rotor has a magnet, right? North, south,
Yes.
correct?
Yeah. Yes.
Yeah. So how does that 90-degree correspond to the north, south, and the created north, south also?
Oh,
Physical to created.
no, 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 no.
No. Physical you have in the rotor, right? You have physical magnet, correct?
Yeah, you have physical magnet. Yes.
Yeah. Now
So
the one we created is through the coils, correct? It will have north, south, correct?
yes, the one
By
we
creation.
created to the
Yeah.
yeah by creation. Yes, you're right.
Yeah. Once you do this
Okay.
90 degrees, how would those would be oriented on both north, south, south, north?
South north. Okay. Wait, let me. I partially understood your question. So let me explain. Now.
So if I can probably say this one, right? So the rotor magnetic field angle, you're going to use,
Rotor
we know the
magnetic
angle
field.
by the sensor, right? You said the
Yes.
yeah,
Yeah.
sensor,
Sensor.
right? So we know, what is exactly the angle of the magnetic field of the rotor. Now,
Yes.
we based off this IA, IB, IC, we know the
Mhm.
angle of the IS.
Stator.
Yes, stator. So
Mm.
all we have to do is apply this IA, IB, IC
Mhm.
90 degrees to whatever the sensor reads out for the rotor.
Mhm. No,
Right?
no, not it. No. Yeah, you are right. But how it is done? I didn't. I only told you the logic of what need to be done. I didn't say how it is done at. Okay.
Okay,
Now
okay.
coming to Tofik. Tofik. Uh,
Yeah.
so Tofik, imagine there is a magnet here, North Pole and South Pole. This is
Yeah.
your
These are fixed, right? Fixed physically,
yeah.
right?
Yes, these are fixed physically.
Yeah.
Okay. And this is yeah, these are fixed physically. And around this, you have three more uh, three more magnets.
Right. Because
Okay.
of the field,
Because of
basically.
the yeah, because of three, there is a imagine there is a resultant here.
Right.
Okay, this is IS. Okay. And this is because of the uh, rotor, and this is because of the stator. Now
Right.
you have control on the currents which are flowing into this one, right?
The
Okay.
stator.
Now yeah, the stator, you are providing the current to them. See here in the diagram, I told you, I in the diagram here, see this VA, VB and VC, you are providing from the inverter to the
Right.
brushless DC motor. So you have the control of VA, VB and VC.
So far, so good. Yeah.
Yeah. Now what I will do is, okay, now angle between these two, okay, this rotor and the stator is not 90 degrees right now. So what I'm trying to do is I'm trying to make this IS by using a control system. What I will do is I'll make this IS I'll make this IS 90 degrees to this rotor.
To the North
This is
Pole.
IS desired.
This is my point. Yeah. So basically, I'm moving the IS side to the S. It's gonna be S, right?
Desire. IS desired. Yes, IS desired.
No, it's gonna be S in terms of simulated
Yeah, yeah,
magnet.
IS. Yeah,
No,
you're
I'm
right,
talking.
Tofik.
No, I'm talking about north south, north south. The same naming convention. Okay, because IS is creating another magnet, correct?
Yeah, IS is creating another. Yeah, IS creates another
Yeah.
magnetic field.
So basically, when you wrote down the tag IS derived, it should be south
Okay,
pole,
desired.
isn't it?
Desired.
IS
Desired is
desired should be
South. You
yeah,
see what I'm saying?
you are right
South,
because it gets
south pole.
attracted. Yeah, South
Right.
Pole. Yeah,
Right.
yeah, you are
That's
right.
what I'm talking. Okay.
Yeah, you are right. I'm only
Okay.
speaking about currents because I because I'm controlling the current by which I'm controlling the north pole and south pole.
Exactly. Exactly.
I'm not speaking about, because magnetic field is dependent upon the current which is flowing through it.
Correct.
Okay,
Yeah.
so here if you
Right. Right.
observe, if you observe this picture, this one, the derivation which we did do. Okay, here if you observe, see, as the current flows into this dotted one and the current comes out of this, you develop this north pole and south pole.
This is the
Okay,
key. Yeah. Mhm.
yeah, so I'm using an electromagnet. I'm not using a permanent magnet here. Okay,
Right.
imagine a solenoid. If you know a solenoid, so what happens in a solenoid? You wind the winding, as the current flows through the winding, you develop the magnetic field in a solenoid. Okay, the same thing happens even in electromagnet. Okay, you have a windings here. When the current flows through the winding, then there will be a north pole and there will be a south pole. Okay, so if I can control the amount of current, okay, then I can control the north pole and south pole.
Right.
Okay, so in electronics or in the electric vehicle, we don't actually speak about, instead of speaking about magnetic fields, we speak about current, so that we speak about
Mm,
current, which in turn controls the magnetic field. That's how, I
I
mean,
see.
that's,
Okay.
yeah, that's what we do. Yeah.
Hmm. Okay.
So here,
Understood.
so say, so these are coils. Okay, as the same formula which I showed you earlier here. The magnetic field or magnetic motive force, FA. Imagine the magnetic motive force is NS by 2 is the number of coils, okay, into IA. See this current. Okay, now I'm controlling this current, or I'm controlling the, I'm speaking in terms of resultant current. Like here, if you observe, there are three currents: IA, IB, and IC. See, these three currents will result in the magnetic field. So, so here I'm speaking about the currents and the magnetic field, because here I'm speaking about how the motor is built, how the windings are made. But whereas here, when it comes to the concept today, which we are discussing, I'm not speaking about the windings, because the motor is already built and I'm enhancing the torque of the motor by applying a control technique.
I see.
Okay, so I'm only speaking about the currents which I can control from the outside. I'm not speaking about the windings, how they are done inside the motor.
They are fixed, you know, so you cannot play
Yeah,
with
they are
them. Yeah.
fixed. Yeah, I'm not playing with them. So, so, so my aim in the field oriented control of a brushless DC motor, today's topic, what my aim is to push the IS to IS desired, so that angle between the stator and the rotor will be 90 degrees. Okay, stator and rotor will be 90 degrees. Now we know this to be done. Then how it is done? There comes another smart mathematician called Park transformation. So I think the name of the guy is Park. What is Park transformation? So I alpha, I beta, okay, I alpha and I beta. You have I alpha and I beta here is equal to, okay, cos theta r sine minus sine theta r, okay, sine theta r cos theta r into id into iq, id into iq. Now from, as you know, ia, ib and ic, you know I alpha and I beta, okay, because here it comes, not here, okay. We know I alpha and I beta. We don't know ID and IQ. So we will do inverse Park transformation. That is ID and IQ is equal to, you take this matrix and you find the inverse. So inverse is cos theta R minus sine theta r, sine theta r, cos theta r, whole inverse into I alpha and I beta. So this is inverse. You apply this Park transformation technique. Like if you simplify it further, if you find inverse for a 2 by 2 matrix, then it is very simple. Cos theta r. Uh, this will be sine theta r. This will be minus sine theta r, and this will be cos theta r. If you find inverse, okay, into I alpha,
So
I beta, and ID and IQ. This is the math we apply in order to find ID and IQ. So this matrix is called Park transformation. Park,
The last one.
yes, the last one is called Park transformation matrix. Okay, so how do you like you know you need to go here, but where is that? What is that? Like if you want to go on a highway, the Michigan government has determined, okay, 75 miles per hour is your speed destination. Here also, like your aim is to go there, like make that IS to IS desire to get the maximum torque. But you don't know what it is or where it is.
Mhm.
So where it is here. Once you multiply I alpha and I beta with this matrix, then you'll find ID and IQ, and your ID is your IS desired.
um, Narendra. So
Yes,
if we go back to that um, picture where you are rotating the IS, right? Yeah, this one, yeah, on the left.
this one
No, the other one. When where you rotate the IS um,
here.
to ID. Yeah, that one. Yeah.
Okay, just
So
a second. Just wait. What? Just a second. Wait, I just want to clarify one more small thing. ID. Oh, okay. This is IQ and this is ID. Okay. Yeah, I made a small mistake. Yeah. Just a second. So this is IQ and this is ID. Just the naming convention has gone wrong. This is IQ and this is ID. Yeah. Please
okay.
ask your question.
So um, you have the IS, right? The blue line. We
Yeah, the
want to
blue
rotate
line
it to IQ,
IQ. Yeah,
right? Okay.
we want to move it to
So
IQ, not rotate
we
it.
want to move it to IQ.
Yes,
So that angle is um, 90 degrees. Okay, so what is that angle? That angle is like 90 degrees minus I theta s minus theta r, right?
the angle is I theta
So that
S
is
minus. No. See, you know this theta R, right?
yeah, theta r. We know the theta
Okay.
r,
Okay.
right? So that particular
Uh-huh.
angle is
You from the
um,
sensor, you know theta R. Okay.
Mhm.
From I alpha, I beta, from IA, IB, IC, you know theta S.
just 1 second. So you have theta s minus theta r is
Sine of
that
theta S
angle.
minus theta. Okay. Sine of theta S minus theta R.
That's what they're using. Okay. If you go back to that picture,
Okay.
so
Okay.
if you rotate it by just theta r, right, it's not going to go 90 degrees. If you simply rotate the IS by just theta r, it's not going to be 90 degrees. 90 degrees to theta theta r, right? So in the see the transformation
Guna,
matrix that you
you're
have.
not clear. Okay,
No, the
transformation matrix.
transformation matrix that you have.
Okay,
C, C theta r minus cos theta minus
sine
sin
cos
theta,
r
sin theta, cos theta, right? So that's a rotational transformation matrix,
matrix. Yeah,
right?
rotational
You're rotating by
transformation
theta
matrix.
r, right? So if you're rotating by theta
Rotating.
r, IS will not go to IQ.
No, no, I'm not saying IS went to IQ. I'm just
Okay,
finding, where IS should be in order to get the maximum torque.
right. Yeah, which is basically
Uh,
when IS is going to be at IQ.
yes, which is going to be when IS is going to be IQ and when ID equal to 0.
Right. So
ID should be 0. Then only you can take it here because you're finding IS projections with respect to the rotor. Yeah.
yeah, so that angle is to rotate the IS to IQ. It is
To rotate
90
IS
minus theta s minus theta r.
90
Minus theta s minus theta minus of theta s minus theta r. The theta s
minus
minus
of
theta r is the IS angle.
theta s minus theta r.
Uh, in front of
No,
it, you
no,
have to
Guna,
have 90 degrees. You have to have 90
no,
in
no,
front of it.
no, Guna. No, this matrix transformation is right. See here, here, theta r is the angle which the rotor is making with respect to I alpha. Theta
Okay.
s, which the stator is making with respect to I alpha. Right?
Yes, okay.
Okay. I am find here. These are not physically available in the motor. Okay. This is my imaginary value where I need to push my IQ in order to get the maximum torque.
I get that. The only thing
Okay.
is, how do you move that
Your
vector, rotate that? How much degree you have to rotate that IS vector?
how
That
much degree how much degree you need to rotate?
yeah,
We will
to yeah,
implement a
to
PI controller for that.
okay,
Okay.
okay.
So okay, we'll implement a PI controller. I'll show you a simulation. Okay. Now, like guys, is this concept clear? I want to go ahead and explain the whole picture of field-oriented control. Any questions on the math or the logic here, which I am applying? Transformation matrices. I don't know how those mathematicians derive that, so I can't
Yeah.
explain that for sure.
No, the main thing
Yeah.
here is so we're playing with the IA, IB, IC to move to IQ,
Yes.
right?
Yeah.
That's
You're
what.
right. You're absolutely right.
Okay.
Okay, now let's take the whole picture of understanding of field-oriented control of a brushless DC motor. Okay, now you have a motor. Okay, you have a motor. To this motor, you connected an inverter. This is an inverter. Okay, this inverter will give you IA, IB, and IC. Okay, now to this inverter. Okay, inverter. Okay, so to this inverter, you'll have three voltages, VA, VB, and VC. Now let's get into a bigger picture of whole how this field-oriented control technique is implemented. So to this inverter, what you will do, like if you take this one, if you take not this diagram, wait, field-oriented control less. Okay, now to inverter. So what I'm saying, to inverter, you connect it to a manual control or a microcontroller. So this microcontroller will provide voltages to the MOSFETs here. See, there are six MOSFETs, or you can consider one MOSFET as a pair. Okay, so there are three voltages which you provide to the MOSFETs, which in turn which in turn provide the voltage to your brushless DC motor. Okay, see, this one is for the MOSFETs, and this battery is for the brushless DC motor. Now here when you take it into a whole picture, okay, so to the inverter you have a battery power supply, DC motor battery power supply. So the voltages which you provide to the inverter VA, VB and VC, how do you get from V alpha and V beta? What I call it as inverse parked inverse park transformation. Inverse park transformation, that is V alpha and V beta. Okay, here you have I alpha, like three currents. Okay, because of these three currents, IA and IB and IC, you'll get I alpha and I beta. Guys, are you clear with this one?
I am not. So
Okay,
shouldn't the V alpha and V beta be output of inverse part transformation?
sorry, inverse Clark transformation, not Park. No,
So you're
no,
giving
Guna.
V alpha and V beta as a
See,
input.
you got confused between. See, uh, no, okay. Just this small confusion. Don't worry. Like here, if you observe from three dimensions to convert into two dimensions, we use Clark transformation.
Mhm.
From two dimensions to three dimensions, we use inverse Clark transformation.
Okay, okay.
Okay, so I'm taking V alpha and V beta. I'm providing VA, VB, VC to the inverter. From there, I'll get I alpha and I beta. This is without field oriented control of a brushless DC motor. Okay, there is no field oriented control technique here. Okay, I'm just saying what it is, just what without obtaining maximum torque. Now to this uh, we're gonna apply park transformation to get the maximum torque. So to get the maximum torque, we need to apply this mathematics to the motor, this one, this logic to our motor. So for that, we know I alpha and I beta from IA, IB and IC. And we also know we need to know theta R. So to find theta R, what actually they do is they have an encoder the motor, or you
The
can
rotor,
say yes,
the rotor, right?
in the rotor. Yeah, in the inside the motor you have an encoder to determine the position of your rotor. Okay, so from here you have IA, IB and IC. Okay, IA, IB and IC, IA, IB and IC, and you apply. Okay, and you apply Clark transformation. Okay, Clark transformation to get I alpha and I beta. You get I alpha and I beta from IA, IB, IC, and you applied Clark transformation. You get I alpha and I beta. To I alpha and I beta, okay, you take the value of the encoder, you get theta R, and you apply Park transformation. And what do you get from the Park transformation? ID and IQ. You got ID and IQ. Now, what is my aim? My aim is to make your IS to IQ. I need to push my IS to IQ, and I need to make ID equal to 0. So, so, so you have two controllers, PI controllers mostly, PI controller, a PI controller. Okay, your desired ID is 0. Okay, and you desired IQ because you want to control the position, uh, the position of the motor. So this is your ID and this is your IQ, and the error you give it to a PI controller. From the PI controller, you'll get ID and IQ. From ID and IQ, what you can do is, again, here, this is ID and IQ, and this is V alpha and V beta. So again, you'll apply inverse spark transformation. And VRSC. This is what a field-oriented control of a brushless DC motor looks like.
Sorry,
Everything
Narendra. So what is PA again? Sorry.
PI controller, or control system, you can say. We didn't speak
What does
about
it
it.
do?
We'll speak in control,
Proportional integration, integrator.
proportional integration controller.
Yeah.
What do we do? Oh, that's it. Okay. You know controllers, right, Guna? You heard,
Uh,
right?
Controllers, yeah, microcontrollers. In
No,
robotics,
micro
robotics use controllers, right? Is
no,
it?
no,
Control theory.
no.
This theory.
No,
Yeah.
that so robotics microcontroller is a chip. Okay,
Yes.
controller is a technique to obtain the desired value. For example, uh, you push the pedal in the vehicle. Okay, your aim is to you push the pedal. Okay, and uh, the speed uh, with which your vehicle is moving is changing when you push the pedal, right?
Yes.
Guna. Now,
Yeah.
now, if you push this much of pedal moment, how will the vehicle know this much speed I need to increase? You understand my question?
Yeah. Yeah. So
So
It's
there
more,
comes a
it's cruise
something
control. Think
called
about
a
cruise control.
yeah
Probably
yeah
easy to
yeah.
think about cruise control, right?
Correct. I couldn't hear you. Can you please repeat?
So it's probably easy to think about it like a cruise control. You set at the point and then automatic adjustment.
Yeah. Cruise
To-
control. Yeah.
cruise control.
Yeah.
Okay.
Yeah.
Adapt
Mhm.
to cruise. Yeah.
Yeah.
You're right. Yeah, adapt to cruise control. Like the vehicle follows the one which is in front of you, right?
Got
It
it.
try to
Okay.
maintain the same distance. See, there is so controller is not hardware. It is the logic which you develop, building a relationship between the desired and the measured.
Mhm.
Okay,
Okay.
so that
Okay.
the logic. So we in the last week I'll tell you. For example, there are two glasses here. Okay, this is heavy. This is not heavy. Okay, but I am lifting them. Okay, so so my brain here will tell me how much force I need to apply. I need to apply in order to move them. See, uh, so the actuator is the same. I mean, my hand is called actuator. In general, a motor or a vehicle or an engine is an actuator. Okay, so which actually or a valve or how much water is flowing into the tank, then that is an actuator. Okay, or a motor which is rotating, it is an actuator. Okay, but here my hands are my actuators. Okay, but my aim is to lift these two until here. So changing the position is my aim. Okay, but the amount of force I am applying is different. So my this hand has a different value. This hand has a different force value. So the thing which determines the amount of force I need in order to lift these two glasses is the controller.
Okay, okay, got it,
Okay,
got it.
that math is going on behind my mind. In the same way, in the vehicle, when you push the pedal, okay, as you push the pedal, how much at what RPM it should like, see, the same engine you might have in uh, Camry and you might have in Lexus. Okay, but with the change in the controller, they can obtain how fast it can reach the set point. Okay, Camry might take to reach 100 miles per hour, maybe 10 seconds, whereas Lexus might take maybe 5 seconds. Okay, how did they do? In the they make modifications in the controller. You tune it better. You try to provide the right values at the right time. Then it will reach the set point. Okay, so that thing, that logic which you implement inside a microcontroller in order to achieve your desired output is called as controller.
Okay.
Okay, yeah.
So there is some
So
logic built in that PI controller that basically.
yes, yeah, there
Okay.
is a logic built in a PI controller that basically uh, that basically pushes that, like, what's the logic is like here, this is the ID and this is the IQ. Okay, uh, you want to achieve, and this is the one, this is the actual ID and this is the actual IQ. Okay, now the error we do, this is plus, this will be minus, this is plus, this will be minus, and this error you'll provide it to the controller, and this controller will say, after going through this math, this controller will say, oh, this much you need to change, this much you need to push, which will be which will give you uh, okay, which will tell you, okay, based on those values, again, what you can, this error, this is called control input. Okay, basically it is represented by u. From this after finding, like, every time it changes, from what technique you're trying to implement.
So it's a feedback loop,
From
right? It's a feedback loop.
yeah, it's a feedback loop. Yeah, you are right. It's a
And then,
feedback loop. For example,
this keeps calculating the difference, and then it applies that much amount of voltage and current finally at the end of
current, yeah,
the day.
yeah, that much of, yeah, you are there. Yeah, guys, any questions on this field oriented control of brushless DC motor? In tomorrow's class, I will go through the torque equation derivation, and then we'll implement this one in MATLAB.
Sounds good.
Okay.
Yeah. Any questions?
Nope.
Oh, we
I
good.
hope. Okay.
Good.
Sorry, guys. There is a confusion. I thought professor covered some things, and sorry for that.
Yeah,
Yeah,
but mainly, yeah, he went over the AC business, the synchronous,
yeah.
asynchronous motors.
Okay. I'll make sure tomorrow we'll go through the torque equation.
Okay.
Then we'll go through the MATLAB. And oh, I want to show you something. Actually, I have a small circuit here. Just a second. Uh, let me uh, let me connect this. Uh, so this is a simple circuit. Okay, I am at my place. That's why I turned off the camera. But let me
Mhm.
connect it, and I will show you a simple circuit. I have a DC motor and a H bridge and a battery. So with the help of the battery and with the help of the H bridge, what I am doing is I'm controlling the speed at which the motor is rotating. So as I told you earlier, so there is a MOSFET. So what this MOSFET does is, uh, MOSFET is like, imagine MOSFET is a switch and the pipe, the valve is the gate.
Dam control.
Okay. and the amount of time you open it, the amount of current flow will be different. If the flow of current is different, then the speed of the motor will change. Okay. Okay, I'm connecting a different USB camera.
Okay.
Okay, yeah.
So one question. So we were talking about all these vacuum cleaners, small appliances having a DC motor. Is it all brushed DC motor or brushless DC motors?
Which one? Small up. Oh,
Yeah.
brushless DC motors are very costly. You can only see in drones. So
Oh, I see. Okay.
and you're not providing. Yeah, yeah. So yeah, I'll show you brushless DC motor also. They are very small. They're mostly used in very fancy applications, not in general purposes. Okay. Yeah. See, guys. So sorry if it's in a bad condition, but still you can see this is a DC motor. Okay, and this is a battery. So here is my control circuit. So what it does is this, with this knob I'm increasing the valve position. For example, if you look at the screen, uh, I explained, right, like in a paper, like just a second. Yes, so look, please, I'm sharing the screen, right? So what
Yeah.
Went away, but
so so
Are you showing the camera or the? Okay, now
no,
you're going
not
to the.
the screen.
Okay.
The screen.
Okay.
oh, screen.
So
Okay.
there
Yeah.
so there is a MOSFET here. Okay. Got the symbol. So there's a MOSFET here, and there is a battery. Okay, connected. And here this is connected to a knob, like, or you can say this is connected to a microcontroller. Okay, microcontroller. This is ground. Okay, what will happen? This MOSFET, like yeah, take this analogy into account.
On
Okay,
off, right?
on off. No. More, it's more like analog. If you move the valve more, then more current will
Oh,
flow,
okay.
more water
PW,
will flow through the pipe,
P-
right?
PWM.
So yeah. So from the microcontroller, you will provide PWM signal. If the PWM value is very high, then the amount of current coming out of the battery will be very high. If the PWM value is low, then the amount of current coming out from the battery will be low. So So this is the general circuit which we use. Based on the application, okay, here I'm having a motor. In a different application, you might have a bulb also. In this case, I used a motor. Now, this microcontroller, with the help of the knob which I have at the microcontroller, I am controlling the PWM signal which I am providing to the MOSFET. So if I turn the knob completely, then PWM cycle will be 100%. Then there will be flow of current at a very high. If the knob is less turned, then the PWM signal will be less. Then the amount of current flowing into the motor will be very less. So the speed of the motor will be very less. So the circuit or the equipment which I am showing is nothing but the circuit. Okay, so the knob which controls the PWM, which in turn controls the amount of current. Why, Narendra? Why we need so much? Why can't we just uh, use a DC power supply where it is very easy to control a current flowing through a motor? Why? Because this is a simple scenario where I have a motor of 12 volts, which is very easy for me. Even though I don't have a microcontroller, it's easy for me to control. Imagine a motor which takes 40 amps current. Okay, so this power supply here, it is 12 volts power supply. imagine it is like 240 volts. Okay, anything above 60 volts is a high voltage. It is considered high voltage because it can kill you. Okay, so imagine a motor which runs at 240 volts. Okay, for 240 volts motor, you don't want to play with the power supply. You don't want to play with the battery. 240 volts power supply. You don't want to change. Don't want to go to the knob and keep
You
changing.
don't want to touch
That's
it, basically.
you
That's
don't
yeah.
want. Yeah, basically, yeah, you don't want to touch. Yeah, thanks for the right word. You don't want to touch it. So what do? You use a switch and you use a microcontroller so that there is no need of manually. Instead of this knob, you can program this microcontroller. If you have taken Neshwan's class, like Arduino, automotive mechatronics, I think he teaches in the PACE, he'll tell you how to program a simple microcontroller. Okay, in that microcontroller, with this, I can program this microcontroller and I can control the switching of this MOSFET. Once I know how to control the switching of the, how to control the MOSFET, I'm able to control the speed. So when I go on uphill, if I need high speed, I'll detect the uphill by using a camera, and I'll tell my microcontroller, increase the PWM. Then it will increase the current. Then the vehicle will maintain the same speed limit. Okay, adaptive cruise. Yeah, adaptive cruise control is the same. You want the engine to rotate at the same speed. So what do? The microcontroller will identify, oh, there is a uphill. Okay, so I need to increase the speed at which my engine is rotating. So the microcontroller or the car ECU, which we call ECU, right, in automotive, the ECU will identify, will get to know, oh, there is a uphill. So I need to increase the speed or the RPM to maintain the same speed. So the same thing here, everything is the same logic. Any microcontroller is the same. You program it to control the switching of your MOSFET, which in turn tells you how much current how much current the motor should rotate. So here the same experiment I'm showing here. So this is the here, instead of microcontroller, I'm using an inbuilt board. Okay, I didn't program it, but the knob here controls the PWM signal. This PWM signal, see, depending upon the PWM signal, the amount of current coming out of my battery will change. If the amount of current changes, the speed at which the motor rotates will be changing. See, to the motor, I have a small pin just to identify speed at which it is rotating. See, if I increase see, I'm increasing the knob push now. See, you can see the speed of the motor is changing. Now I'm reducing the knob. Now the speed of the motor is reducing. Can you identify can you listen to the speed? Sorry, guys. Guys, are you able to
No,
listen
maybe
to
the,
the speed?
yeah, I think
Yeah.
microphone basically filters out those noise.
Yeah.
Yeah.
Okay,
Mhm.
okay. But can you at least see the pin the
Yeah,
pin?
I can
Yep.
see that it's rotating. Yeah.
Yeah. Now I see that.
Yeah.
Yeah.
Oh, this is a
Now it's
simple
moving faster.
experiment.
Yeah. Now
Yeah.
it's
Yeah,
moving
it's moving
faster.
faster.
It's faster.
Yeah, not a complicated one, but here I want to identify, okay, how with a small knob, even this motor is only 12 volts motor, even though 240 volts motor also you can control by using this technique. All you need to do is find the right MOSFET. That's it.
So
Okay,
this
that's
is a
why.
brushless DC motor, Narendra?
No. This is a DC motor, just DC
This
motor.
is this is a
Brushless DC motor.
cheap decimal, right?
Okay, okay.
Yes, yeah, cheap DC motor. Yeah, you're right.
Mhm.
But good for an experiment. It's a 12 volt
Right.
DC motor.
Okay.
Yeah, tomorrow I'll show you brushless DC motor.
Okay.
Okay.
Oh, this is a
So what is
simple technique.
PWM?
See,
What is
so
PWM?
so again,
What does it stand
yeah,
for?
oh, pulse with modulation.
Oh, okay, okay.
Okay, so I mean, it's a different subject, but I can still like think of this analogy here, this analogy. So if you want to move this remove this valve completely, okay, imagine you're providing PWM signal here. PWM is basically a square wave. See, at high frequency, a square wave signal will be coming out of this microcontroller, something like this, very high frequency. Here. Okay, so what will happen is when you provide this signal, okay, the average of the signal will be considered by
Is the
your
width changing?
MOSFET.
When you go
Yeah.
from 0 to
Uh,
highest rotation.
yes. If okay, wait. Yeah. Okay. In general, as you increase for this experiment, if I changing the knob position, then the width is changing. Otherwise, it is not.
Okay, got it.
Okay. Okay. See, for example, most MOSFETs, they operate at 0 to 5 volts. Like if you apply 0, that means this valve is closed, no current will flow. Or you can say switch is closed, no current will flow. And if you apply 5 volts, then this valve is open, then the current will flow. The complete current will flow, or 100% current will flow to the maximum capacity.
Thanks, Narendra.
Are you with me? Okay.
Yeah,
Now this 0 volts to 5 volts, you need to have control. This is given by PWM signal. How how it is given by PWM signal? See, basically the microcontroller will operate at a frequency much very much higher, like in kilohertz might be. So, for example, this 0 to 5, like 0 to 5 volts is the maximum value, is the limits of your MOSFET. Okay, is the limits of your MOSFET. Okay, now what will happen is, for this is the duty cycle. If the like on this is, if you take one cycle, one full cycle. Okay, so here it is on for 40 percentage and it is off for 60 percentage, right?
Mhm.
Okay, again, now I didn't draw in a right way, so it is on for 40 percentage. So 40 by 100 into 5 volts, like I'm giving a rough estimation. Okay, so 200, okay, by 100, so you're providing 2 volts. So the wall will be open only 40 percentage, or you can imagine like wall will be open only 40 percentage. Or if you apply 2 volts, the wall might be open only like depending upon how much voltage the wall will open, right? For example, if you want 5 volts to pass through, then you'll give a PWM of duty cycle 100. Okay, then how it will be like on. Okay, then the average value which you gave is 100 percentage. That means the total 5 volts you're applying. Or if you want to apply 3 volts, then your duty cycle will be different. Okay, there is how wait.
Yeah, that's very
Okay.
clear, Narendra. I don't want to hold the other guys. Means 6:40 already.
Yeah, good
Okay.
point. Yeah.
Yeah, guys, any questions on today's topic? I'm
Thanks. That's
done.
good.
Guys, any
Yeah,
questions for today's topic?
yeah, I'm good. Thanks, Narendra.
Yeah, Guna, if you have still questions on
Thank you.
PWM, you can stay. Yeah.
All right.
Yeah,
See you
truck.
tomorrow.
Yes,
Thank you.
tomorrow.
Bye bye.
Thank you.
Thank you.
Thank you.
Guys, if you have any questions, you can stay. I'll be here.
Thank you. See you
Thank
tomorrow.
you. Bye bye.
I'm good, Narendra. Thank you. Really
Okay.
appreciate it. Have a great evening.
You too.
Hi Narendra, this is Chandra. I just joined late today. Cluster cooling
Okay,
grounds, so I was driving and stuck in the traffic for 2 hours.
it's okay.
So I missed that first. I get if at all. I think that this class is being recorded, right? I will go through that
Yes.
recording and then if at all if I have any doubts, maybe I can come back to you or I can check with the Guna itself.
Yeah. If you
So I
don't
and Guna
understand,
works in
we
the
can
same
have a
team. Sure.
one-to-one meeting and I'll
Sure.
explain you. Okay.
Okay.
Yeah.
Thank you so much.
Yeah.
See you tomorrow.
See you.